Hey guys, welcome back. Today we're going to continue on from the lecture that we did from section 8.3, except this time we're going to do constant coefficient linear differential equations, the non-homogeneous version. That's much more fun, right? As normal, we'll talk about some required skills first, and in this particular case, just a couple of required skills. The first is that you're able to solve the homogeneous version of these. That's actually going to be very important for us. All right, so we need to know how to do the homogeneous version. If you're watching these videos out of order, again, we covered how to solve the homogeneous versions in the previous lecture. Okay, so I assume that you guys know how to do that. Look up the homogeneous version if you need to. I think it's 8.2. Yeah, that's 8.2. Okay, we also need to be able to solve for undetermined coefficients. This is just a fancy way of saying if I have an equation and it's got several unknowns in it and there's enough information in that one equation to solve for several unknowns, can we do that? And we can. I've shown you an example over the semester, but just for our purposes, I'll make sure I'll put an example in at the end where we've got several unknowns we have to solve for, and that's it. Okay, so let's talk about maybe the theory and how we're going to do this. We had discussed for the homogeneous version that, so this homogeneous version of this is some linear transform applied to y equals 0, right? Where this linear transform is a polynomial differential operator. And now we discussed that what we were really looking for is, we're really looking for the kernel of this operator, right? I know this operator maps Cn to Cn minus k, some collection of functions which have some continuous derivatives to another collection of functions that have continuous derivatives, some fewer continuous derivatives. And I was looking for the kernel of those things, right? And again, just to sort of give a concrete example, we had something like, I'll use d squared plus 1. There's my linear transform. And y gives me 0. Okay? And we were able to use the auxiliary polynomial and its roots to come up with, again, my general solution as c1 cosine x plus c2 sine x. And again, this is the kernel of this particular linear transform. Okay. But if you remember back to our short little module we did on linear transformations, I know that if I have a linear transformation which maps one vector space to another vector space, and again, Cn is a vector space for all n, then I know that in effect what that linear transformation is doing is that it is dividing up my domain into copies of my kernel, okay? So if I ask you, and this is a very similar question here, if I ask you now this equation is almost identical to this with the sole exception of the fact that it's no longer homogeneous. Instead of 0, I have some other function here. Well, it makes sense, really, that if this entire space in my domain got mapped to 0, right? So this is a two-dimensional space. You can think of it as a plane, right? If this two-dimensional space gets mapped to 0, well, this linear transform, it chopped this original domain into several copies of this space, okay? And so it makes sense that the solution here would be a copy of this plane shifted by just a little bit, right? So I either add or subtract a small amount. In this particular case, we're talking about a small function, okay, to those things. All right, and then that kind of makes sense. So let me talk about what this is actually saying, and I'll give you a proof for why it works. That little bit of extra that we're looking for when solving a non-homogeneous version of these differential equations, okay, that little bit is called my particular solution, right? So here, for this particular equation, I know what the solution to this looks like. I get for, let's say, y1, y2, all the way to yn. Suppose this is a linearly independent set of solutions to this particular linear transformation. I make my general solution as the linear combination of these two things. So for some appropriately chosen constants, C1, C2, etc., C1 times Y1 plus C2 times Y2, all the way to Cn times Yn. Every solution for this can be written in this form. Okay. So again, what I'm looking to do then is I'm looking to build off of this solution. This is the solution to the homogeneous version. I'm looking to build off of this. Well, okay, all right, fine. So, and remember, if I take something like this and I plug it into L times Y, I'm going to get 0. So something that looks like this is not a solution here. Okay, but let's say I do have one, right? So, maybe suppose Y sub P is a solution to L times Y equals F, right? So this is I found one, right? Maybe it was by trial and error. Maybe it was by the method of undetermined coefficients. We'll do that later on in this lecture. But again, suppose I found one of these, okay? And suppose further that I have, I'm going to say U is any solution to my non-homogeneous equation. Now what I'm looking to do is I'm looking then to figure out a way that I can write U, because U is any possible solution, right? I want to figure out a way that I can write any possible solution to this differential equation, just like I wrote any possible solution for this differential equation. Okay, well, let's maybe consider these. Okay, so I know then that L of U minus L of Y sub P. Okay, so these are both solutions to this equation. So these are both F. So that's F minus F. Okay. All right, fine. Now this is, of course, a linear transformation, and because of that, its linearity, it is both scalar invariant and additive. Okay. I know then that this is the linear transformation of U minus Y sub P. Of course, that's how my linear transformation works. And F minus F, of course, is just, well, nothing. Okay. And so if I look, I now have this same linear transform I have here, same linear transform I have here, that it applied to this function is equal to 0. Well, that's this differential equation. So I know what U minus P must be of this form. Okay, so U minus Y sub P must be C1Y1 plus C2Y2 plus CNY sub n for some C1, C2. I mean, might have to appropriately choose my C's, but yeah, I can write this in that form, okay? Because again, this is a solution to the homogeneous version. But if I just rewrite this, I can see that U then can be rewritten as C1Y1 plus C2Y2 plus CNYN plus Y sub P. Yeah, so if I look at what I have here, I've now taken this is just the general solution for this particular differential equation. I was able to take that general solution and I was able to write that as a sum of two different things. I was able to write it as a sum of this, okay? This is the solution to what's called the associated homogeneous differential equation. So that's my non-homogeneous version. This is my associated non-homogeneous, associated homogeneous differential equation. Okay. And the solution for this we call the complementary function. Complementary function. E, not I. Okay. Now, because of that, your book uses, and so I'll just sort of maintain that that same notation. Your book calls this y sub c, right? So this here is y sub c, and notice that my general solution for my non-homogeneous equation is just y sub c plus some particular solution. Well, it seems like we have most of this stuff already then, right? Because the previous lecture showed you guys how to find the homogeneous versions, right? It showed you how to solve all the homogeneous parts. You should be able to find the y sub c already. The only thing we have to worry about then is, how am I supposed to find y sub p? Okay. All right, so for the rest of this lecture, that's what we're going to talk about, how to find y sub p. Now, we're going to use a method called annihilators, and I'll show you a few examples. I'll probably start with a concrete example so we can sort of see where these things come from. And then I'll talk about, obviously we'll troubleshoot after that, right? So we'll talk about what may go wrong during this process. Okay, so let's take a much more concrete example here. All right, let's look at. Okay, so let's look at. Let's say y double prime. Let's go with minus 3y prime minus 10y equals 4e to the 3x. There we go. Okay. Okay, so again, two pieces to this. The first piece is, well, what's my complementary function, right? What's the homogeneous version of this, right? Okay, well, we can solve that pretty easily. Okay, so let's go ahead and solve the associated homogeneous equation. Okay. So rewriting this in my linear transform notation, that's d squared minus 3d minus 10 y equals 0. The auxiliary polynomial for this is, of course, just r minus 5 r plus 2 equals 0. Now this has two roots, of course, 5 and negative 2. This gives me, of course, my two trial solutions here, e to the 5x and e to the negative 2x, which in turn, of course, allows me to say that my complementary function here is c1, that looks like an e, c1 e to the 5x plus c2 e to the negative 2x. Okay, so that part's done. Okay, so I feel like I'm most of the way there, although you might notice I left a lot of empty space here for finding y sub p. I feel like I'm most of the way there. All I need here is to find y sub p. All right, I need a particular solution. Okay, fine. So what would a particular solution be? Well, what I'm going to look for is what's called the annihilator. I'd like to know what linear transformation annihilates this function. Okay? Now I'm going to give you guys a list of annihilators here in a second, but I'll go ahead and spoil it so that we can, for this one, so we can see what works for this. The annihilator for 4e to the 3x is d minus 3. Now that might look a bit suspicious. I claim if you apply that at 0, we're going to check it here in a second. That might look a bit suspicious because, if I factored this, I'd get d minus 5d plus 2, right? That's the same thing as my auxiliary polynomial. But that d minus 5, isn't that responsible for r minus 5, which in turn is responsible for e to the 5x, right? You could go backwards. e to the 5x meant that r minus 5 had to be here, and that meant that d minus 5 had to be a factor, right? So this is e to the 3x, and I've got d minus 3. And it does work, okay? Let's actually work this out. This says take a derivative. So the derivative of 4 e to the 3x is 12 e to the 3x, okay? Minus 3 times this function. 3 times that function is 12 e to the 3x, and 12 e to the 3x, yeah, it works, okay? So this is called my annihilator. Now, I'm going to talk about why we want our annihilators here in a second, but I'm going to erase this for a moment and give you a chart. Now, the list of all the annihilators you'll need is located on pages, hold on. Here we go, 518 and 519 in your book. I'm going to write them all down here for you, but again, in case you wanted an easy to look up reference, okay? So let's talk about the functions that we deal with most often and their associated annihilators, all right? So here's my function, and here's my annihilator. Okay, so my function, we just discussed that e to the ax, that's d minus a. Okay, fine. Okay. All right, so what about cosine and sine, right? Well, again, what would have generated cosine or sine? What would have been a polynomial, an auxiliary polynomial with complex values? And so again, very specifically, I can say that cosine bx, sine bx is going to have the same annihilator, right? Because they both come from the same function. You get a plus or minus bi. You always get both, the conjugate roots there. So these are going to have the same annihilator, and that annihilator is d squared plus b squared. Of course, the roots of this are plus or minus bi, giving me cosine bx sine bx. Okay. The only other thing we really talked about were polynomials. Okay. So how about something like a naught plus a1x plus a2x squared plus anx to the n, right? Well, it's polynomial. If you take enough derivatives of it, you don't have to do anything special. If you just take enough derivatives of a polynomial, it's going to be 0, right? So how many derivatives does it take? Well, let's see. Well, let's take a quadratic. So a quadratic has x squared as its largest term. You take a derivative of a quadratic, it becomes linear. Take a derivative of a linear function, it's constant. Take a derivative of constant, it's 0. That's 3 derivatives, right? So degree 2 requires 3 derivatives, and in general, it takes n plus 1 derivatives to annihilate a polynomial of degree n, right? So degree 6 polynomial takes 7 derivatives, that'll be 0, okay? All right, so we did some more, slightly more complicated functions. We had extra solutions, right? Solutions of higher multiplicity. And that created these expressions where I had one of these functions and it had some extra polynomial terms attached to it, right? So things like e to the 2x, x, e to the 2x, x squared, e to the 2x, et cetera, et cetera. So how would I annihilate a product of those things? Well, again, just go back to how this was created. In order for this to have been a solution, right, you had to have had d minus a, that's what would have created e to the ax. But you had to have had that multiple times, right? Because it had to have a multiplicity larger than 1. How many times? Well, in order to get to n, you had to have n plus 1 of them, right? So d minus a to the n plus 1, yeah? And in general, this particular, notice the relationship between this one and this one. In general, if you would like to annihilate one of these functions that has a polynomial multiplied to it, a polynomial term, you just raise it to the n plus 1 power. So again, just to fill out the rest of our chart, if I have x to the n cosine bx or x to the n sine bx, both of those have the same annihilator as before. They've got d squared plus b squared to the n plus 1 power, so same. All right, now, There's one other product we haven't talked about yet. Well, what if I have an exponential function multiplied times a trig function here, sine or cosine? So what would the annihilator for, I kind of used too much room for this. Yeah, I'm just going to write it down here. All right. So if I write e to the ax, crap. Let me move this up. I'll move this one up, okay? So x to the n cosine bx and x to the n sine bx. Okay, here we go. So if I have e to the ax cosine bx and e to the ax sine bx. Okay, so the only real difference here is that I'm looking to be able to create the roots a plus or minus bi, but again, I need those from a real valued polynomial here. I don't want to have complex valued polynomials. So the real valued polynomial, which has both a plus bi and a minus bi as its roots, is, so here's the annihilator, it's d squared minus 2ad plus a squared plus b squared. Okay, hopefully you guys can't hear my son. He's losing his mind. It's nap time, and he does not want to be taking a nap. Okay. So we just have to have these learned, right? I mean, it is what it is. When you need the annihilator, you need it. So again, it's kind of easy to remember. These are the things that would have created these as trial solutions. So the things they have a nice pairing. Okay, now let's go back to the problem we were working on. Okay. Specifically, we want, again, of this type, we want this annihilator. So I would like to find y sub p. Now I'm going to do so by using my annihilator here, and I'm going to put out some extra checks here. So let's see, y sub p. All right, so the annihilator for the non-homogeneous portion is sorry, that sounds really hot. He's really laying it on. So the annihilator here is d minus 3. Okay, it's a bit of a glare. I'm trying to reduce the glare on this. Is that better or worse? It's mediocre. I don't know. We'll do what we can. All right, so the annihilator is d minus 3. Now, d minus 3, this corresponded to the trial solution e to the 3x, and that makes sense, right? Because I want my particular solution would probably end up creating this. But I have to be very careful, right? To be very, very careful. I need to ask myself, is this factor already present in my homogeneous version? Because this, whatever I write down as my particular solution, has got to be linearly independent from all of the things I wrote down for the homogeneous part, right? So if I had d minus 5, hypothetically speaking, okay, if I had d minus 5, okay, then I can't make my particular solution some arbitrary constant times e to the 5x, because this is not linearly independent from this. Okay? This is e to the 5x as well. I would have to make it an arbitrary constant, x e to the 5x, right? Because this would have been the second time that d minus 5 would have appeared in this linear transformation. But in this particular case, and I'm going to do an example where that actually happens here in a minute. In this particular case, it's d minus 2. Oh, sorry, d minus 3. D minus 3. Okay? Which makes my particular solution here some arbitrary constant times e to the 3x. Now, you may have noticed I didn't use c, I used a. Why did I use a? Because these constants are, these are the undetermined coefficients, these are the unknown constants that are going to serve in my actual answer. So C1 and C2 are still going to be there in my final answer. I have to find this. Okay, this coefficient here I can't leave as an undetermined coefficient. I have to actually find out what A naught is. How the hell am I supposed to do that? Well, this is a particular solution. Of what? Well, of this. If I plug this into this equation here, it should work out. Well, that's all I have to do then. I just have to take this function, plug it in here, and solve for a naught, right? And if I have more than these, say a1, a2, a3, I'll have to solve for this as well. So word of advice, it is much easier to do this by actually just finding all your relevant derivatives and then plugging everything in all at once, right? So I know that I'm going to need y prime and y double prime. I'm going to go ahead and find those before I actually start messing with plugging these things in and working with the algebra, okay? So let's see. The derivative here would be 3 a naught e to the 3x. The second derivative would be 9 a naught e to the 3x. Okay, so let's take these things and substitute them into my original equation. Okay? All right, so let's go ahead and substitute those in. Y double prime, that's 9 a naught e to the 3x, minus 3 times y prime. Y prime is 3 a naught e to the 3x, minus 10 times y, okay? Minus 10 times y was a naught e to the 3x. And supposedly, this is equal to 4 e to the 3x. Okay. Well, let's see what I have. If I combine all of my terms on my left-hand side, they're all like terms. This gives me negative 10 a naught e to the 3x. That is supposedly equal to 4 e to the 3x. And clearly then the coefficients themselves must be equal since the exponential portion of these terms are equal. That tells me that negative 10 a naught has got to be equal to 4. So a naught has to be equal to negative 2/5. And there we go. I have my particular solution. My particular solution is negative 2/5 e to the 3x. Okay, well that works. So let's see. What's the solution for my differential equation then? Well, my general solution is, remember the construction here, it's the complementary function. So this one, the solution for the homogeneous version. So C1 e to the 5x plus C2 e to the negative 2x plus my particular solution, which is negative 2/5 e to the 3x. All right, that's it. This is here's my solution. This is fantastic. It's not terrible, right? Yeah. Okay. So what happens when this gets a little bit messier? We're going to do one of those in a second. But let me talk about where students tend to mess this up. One, these can get long, right? We've talked about that before. There are two ways to make a problem difficult. I can make it complex, or I can just make it very large, right? And these things can involve a whole lot of algebra, a lot of mashing terms together, right? And then we can make some small mistakes. We don't want to do that, so we're going to work very carefully, right? Very methodically, and we'll make sure that we get all these correct. Okay, let's do another version here. I want to do a version where maybe some less nice things happen with the with finding the particular solution. Okay, ooh, I'm going to start cleaning this thing. Get very dirty. Okay. All right, so that did not help. Did not help at all. To get some whiteboard cleaner. Okay, so let's do d squared plus 1y equals 3 cosine x plus 4 sine x. Okay. Again, non-homogeneous. The first thing I want, my complementary function, that comes from my associated homogeneous version of this equation. That should be pretty easy. Okay, that is d squared plus 1 y equals 0, giving me r is equal to plus or minus I. Okay, I remember r squared plus 1 equals 0, so that's r is equal to plus or minus I. This gives me a complementary solution here of C1 cosine 1x plus C2 sine 1x. There we go. Okay. All right, fine. But again, this is the easy part, right? How do we find a particular solution then? Well, let's see. All right. So always look at your annihilator, right? Always look at your annihilator. I realize that what comes out of your particular solution is almost always going to look exactly like this, right? It's going to look like that a lot of the time, but it won't always, and here's an example of when it won't. The annihilator for cosine 1x is actually the same annihilator as sine 1x, so the same annihilator works for both of these. The annihilator is d squared plus 1. Yeah, but where have I seen that before? That's one of the factors of this polynomial, right? This isn't the first time I've gotten d squared plus 1 in my solution. I can't write my particular solution then as, right, so this is not okay. I can't write my particular solution as a naught cosine x plus a1 sine x, because this is not linearly independent from this, right? This is the second time I've gotten this, and so what I have to add in here, this is my particular solution. Okay? Remember, multiplicity larger than 1, this is what we have to do, right? So my particular solution here is going to be a naught x cosine x and a1 x sine x. Those extra x's are in there. They're also, unfortunately, kind of a pain because I got to take a bunch of derivatives to plug this thing back in. Remember, d squared, I got to solve for a naught and a1 by plugging it back in here, but d squared represents the second derivative of this. So, fine, all right. Let me go ahead and take a couple derivatives so we can see what it is we're working with. So y prime, that's going to be, okay, take a derivative here, that's a naught cosine x minus a naught x sine x. Again, product rule, derivative. Here we go, derivative here, that's a1 sine x plus a1 x cosine x. Okay. I need one more. Again, I need the second derivative. Sure. So second derivative of y sub p. Okay, so let's see. Derivative here. This is negative a naught cosine x. Oh, ugh. Negative a naught sine x. Ugh. That's why you got to be careful, right? So negative a naught sine x. Okay. Again, this is another product rule, so minus a naught sine x minus a naught x cosine x. Okay. Derivative of a1 sine x, that's a1 cosine x. Product rule here, that's plus a1 cosine x minus, so one more term, I'll put it down here, minus a1x sine x. Now I've got some like terms here, and I'll combine those. Well, I'll combine them once I substitute. I'm kind of running out of board space, but see that I've got negative a naught sine x and negative a naught sine x. That's going to be negative 2 a naught sine x, and the same thing here, right? So these things can be combined. These two will be combined. Let me actually substitute it. So go ahead, substitute. All right, so be very careful. I'm going to substitute the whole thing. This left-hand side says second derivative of y plus 1 times y. Okay, so second derivative of y is this. That's negative 2 a naught sine x minus a naught x cosine x plus 2a1 cosine x minus a1 x sine x. So this is all y double prime plus y. Okay, fine. Y is, so plus, here was y, so plus a naught x cosine x plus a 1x sine x. And all of that is supposedly equal to 3 cosine x plus 4 sine x. Okay. Okay. So there should be enough information in this equation to solve for both a naught and a 1. I know there's 2 unknowns in here, but that's okay. And it starts with some simplification. You'll notice that I have negative a naught x sine x and positive a naught x sine x. And I also have negative a1x sine x and positive a1x sine x. So that simplifies this very nicely. And all of a sudden I've got many, many fewer terms, right? So the only thing left over after that is I've got negative 2 a naught sine x plus 2a1 cosine x is equal to 3 cosine x plus 4 sine x. Well, what this is telling me is that the right-hand side of my equation has 3 cosines and 4 sines. Well, if they're equal, then the left-hand side of my equation has to have 3 cosines and 4 sines. The coefficients for these things have to be equal, right? So this, it looks like one equation, but really it's giving me 2 distinct pieces of information. This equation is not only equating these 2 functions, but it's equating the number of cosines and the number of sines on each side of my equation. So I can tell you then that the coefficient for cosine on the left and the coefficient for cosine on the right are the same, okay? So that tells me 2a1 is equal to 3. Well, then a1 has to be 3 halves, okay? And further, I can tell you, a different color here, I like purple, okay, that the coefficient of sine on the left and the coefficient of sine on the right, those also have to be the same, okay? So negative 2a naught, that's got to be equal to 4, okay? Hence, a naught is equal to negative 2, okay? This gives me my particular solution, right? It's this function, a naught's negative 2, a1 is 3 halves. And then taking my particular solution and my complementary solution here, we can now write the general solution for my differential equation. So let's see. It's my complementary solution, c1 cosine x plus c2 sine x. Plus my particular solution, this with these coefficients, right? So plus negative 2 a naught, good Lord. A naught is negative 2, sorry. Negative 2 x cosine x plus 3 halves x sine x. All right. Yeah, all right, so there's our solution. Okay, so again, these are not necessarily terrible. It's just some algebra, right? Just a little bit of algebra that we have to work through here. And this sort of reasoning we have for taking a non-homogeneous differential equation, taking the solution for the homogeneous version, and then adding a particular solution. This is going to persist, so we'll do this a few more times with some other different types of equations later on in the semester. All right, as normal, I'll take some homework. I'll post that online for you guys and under Canvas. And if you have questions, again, let me know in our meetings.